So this is the same complete as here, okay? Which are harder than any problems here. Any of your problems. Okay? Any problem that you can solve in polynomial time, these ones are harder than these ones. These ones are harder. And harder in the sense that you can reduce the resolution of any of these problems to the resolution of this one. Okay? So we are able to find some problems here, but we know that anyway, if we are looking for an hard problem, these are the candidates. These are the ones. Okay? So we don't know much more. I mean that we are not able to prove that these are really hard. We just know that they are harder. But we also know that nobody could solve them until now. Okay? And that's a fairly unsatisfying but reasonably not too frustrating result. Okay? And that's exactly what's going on here. I mean that what's going on here is that as soon as you're able to emulate Boolean circuits, then you're harder than any of these polynomial time problems. Okay? And there are some strong conjectures based on the fact that we are unable to do better than that, that if we would be able to get the result faster than just executing all the steps of life, then we would be able to solve much faster than polynomially, than in polynomial time, this problem here. And we believe it's not true. Because, well, we tried and it didn't work. It's not very convincing, but, you know, there were some pretty bad guys who tried, and anyway. Okay. So basically there are some, this is not the same kind of result as before. Okay, before we had a proof that just tell, okay, this is undecidable. Now we are entering in a less straight world where things get a little bit fuzzier. Okay, but still there is a strong, widely belief that this will not be possible. Okay, but it's not a proof, but it's still widely believed. Okay, so basically what's going on here is that even printing the color of a cell in a cellular automata, we cannot do it. We cannot do it faster than just running the cellular automata. So that's really problematic. It's much, you know, there is some graduation in what we've seen. So first, that we needed to know the exact initial configuration. Okay, that's fair enough. Second, that math could not prove everything. Okay, who cares? Second, that first, so what did we? So as soon as we are too incomplete, then there are things that we will not be able to prove. So it starts to get annoying because these are things that we are really willing to prove. Okay, we want to show that the dynamical system will ultimately reach the paradise or whatever you want to put it into. And now, even the things that we are able to, that we know that we can decide, we cannot decide it beforehand. We cannot do faster than nature. Modulo some conjectures. Okay? So, that's pretty embarrassing. Especially, what is more annoying is that we have pretty stupid programs that are very short. That do things that are just completely crazy. This Mandelbrot fractals is just a silly thing. Okay? You want to call it complex, okay, but when you look at that, you cannot be. Okay? So there is some kind of, you know, hiatus between what you expect to be complex and what really works. Okay? So this is not always only fractals. You have sum-piles. Okay, sometimes it's a very stupid systems where, you know, you just drop brains, okay, on one cell, okay, and as soon as there are more than as soon as the central cell has more than four grain than the others, then the grains drops evenly around it, okay, and you get these beautiful patterns that nobody is able to analyze. Okay, so it's a very stupid one. So you have this universal rule, okay, where you know that we won't be able to prove anything. So the rule is completely stupid, and you have only two states, two neighbors. So basically, you have 8 transitions. Okay, you have for what you need to do. What you need to know to describe this automata is what if the state of my left neighbor is, what is my state, and what is the state of my right neighbors. So there are 2 by 2 by 2, 8 possibilities, and that's it. Okay, and you have completely described the system, and this is universal. And you can simulate everything. Okay, and you can even find cellular automata in natures. So, for instance, here you have the shell here, and it pretty looks a lot like this cellular automata. Okay, so there is some kind of computation going on here. So let's. What time is it?
10.
Okay. So let's make a conclusion for this first part. Is that universal computation is a problem, okay? Because it requires only a very small complexity. Very small dynamical systems are Turing complete, and in that case, a lot of things becomes rather than everything. A lot of things becomes undecidable. This doesn't mean that we cannot prove things on this undecidable stuff, okay? But there are properties that we won't be able to prove, that we would be willing to prove. So we have to be careful. And the worst thing, this is some kind of worst kind of example, is that you can generate universal cellular automata at random with probability 1 minus O of 1, even if it's undecidable to decide whether it's universal or not. I mean, so let me explain. So there is a specific kind of cellular automata which are named captive. Okay, captive means that the only state you're allowed to go to, okay, when you change your state, has to be chosen between your neighbors and you. Okay, if you are only surrounded by red state and you're red, you cannot change your state to something else than red. If you are surrounded by red and orange, okay, and you're green, then the only possibility for you is to go red, green, or orange. Okay, you cannot invent a color that you cannot see. Okay, so this sounds like a limitation, but it turns out that if you do that and draw some randomly this cellular automata, you can prove that with probability 1 minus something that tends to 0 as the number of states increase, you will get universal computation with probability 1. But you won't be able to decide whether this specific automata that you've drawn is universal or not. Okay? So this is some kind of good news, because basically you are in a situation where you can tell something even if you cannot verify it. Okay? Sounds like politics, but anyway. It's just to say that we can still prove things on undecidable stuff. Okay? But you will never know. Okay? No. And the worst thing, to my point of view, is that even if you are in the best condition, that you know the initial condition, you know everything, okay, this doesn't mean that you will be able to go faster than nature. Okay? This doesn't mean that you will be able to predict the weather before it occurs, okay, or significantly before. I mean, you may just get something, forecast it twice as fast, but no more. Okay. So basically, what's going on here is to tell you that, when you think about computation, the dynamical system as computation, you immediately see that you have to be very careful when you design model, because as soon as your model is too powerful, then you won't be able to prove anything relevant. Okay, so that's why, for instance, the easing model, the whatever model you want are so successful. Okay, these are such stupid things, but these are first really hard, already very hard. Okay, but if you would add a little bit more stuff, then it would turn out to be Turing complete, and you could not be able to say anything. So that's the first thing. So I suggest that we take a pause now, and then we will try to define complexity and see how it's related to randomness. Any question?